Hello friends and welcome at my channel. Today I'm starting a new playlist about convergence. I would like to explain some basic ideas about pointwise and uniform convergence, and let us maybe start in the first video with an understanding of what is actually wrong about the pointwise convergence. So what is pointwise convergence sequence? So a sequence Fn is pointwise convergent. Let's write it this way. X is running towards R. If there is a limit n towards infinity and the fn's of x, there is some limit function f of x like this. So can we compute it somehow? I mean, do we have some examples and do we have some troubles maybe about those kind of functions? And the answer is yes. It's not quite satisfying what we're having. So let us see what's going on. If we have f of n, for example, fn of x equals to, let's say, x to the power of n divided by n squared. So what will happen? Do we have a limit function here? Sure, if x is from, let's say, -1 to 1, then there is a limit n towards infinity of x to the power of n divided by n squared, which is basically 0. No problem about that. But what is wrong about the pointwise convergence? Well, the thing is, you see, if we have this kind of always happening example, fn of x equals to x to the power of n, and x is from the interval 0 to 1, then, well, if we consider x between, so n to be 1 first of all, then we just have straight line, which is 1 at 1 and 0 at 0. So everything is fine. If we have x squared, so if n is becoming 2, we have such a function. If we have a cubic function, it becomes even flatter and then it goes up. And so on. So what is happening actually is the function remains longer at the floor level, and then it rises up. And the further we get with the n, the higher the function is going. So that's what's happening. All right. And the thing is, if we're considering now the limit of fn's of x, and n is running towards infinity, we have a problem, because at 1 we're always 1. So it's 0 if x is unequal to 1, and it's 1 if x is equal to 1. And that's the problem. So what is the problem exactly? The problem is this function is continuous, and this one is not continuous. Okay? That's the problem. And this is one of the problems we're dealing with. What is another problem that we also have? Well, the second problem is if we have a derivative of a function which is in a pointwise converge sequence, then it can happen that the sequence is convergent, but its derivative is not. And this is kind of strange, because derivative is always about finite values of the slope and so on, and then something goes wrong. So let us see one more example. We consider fn of x equals to 1 divided by n times sine squared, or sine of n squared of x, in order to get the derivative easier. So what is getting wrong here? Well, first of all, what is the limit of fn of x if n is running towards infinity? Well, you see, the sign is never over 1, so the highest value we can get is 1. And, well, 1 divided by n is getting the whole fraction equal to 0. So the limit is 0. But what about the derivative? fn prime of x? Well, we need to do the chain rule. We have 1 divided by n times the cosine of n squared of x times the inner derivative is just n squared, right? So we just cancel those two and we're gonna get n times the cosine of n squared x. And you see, if n is running towards infinity, we have no limit in here. So this is one of the biggest problems we have. So this is not limited. There is no limit of fn prime of x and towards infinity, even though the limit of f of n of x was given through 0. Alright, so one more kind of trouble that we have. So the frequency is convergent pointwise, but the derivative of this frequency is not convergent. It's a huge limitation for our computations later on. And the third case that we could also consider is, well, let's take maybe one more function. Let's take a gn of x equals to, well, maybe it's the same, 2n squared x, and then 1 plus n squared and x squared, and the whole stuff squared. Why do I do this? Well, you see, it's always nice to have a derivative of the denominator in the numerator, which I'm kind of having here. So if we consider this one, what is first of all the limit n towards infinity of gn of x? What would be the result? Well, it's obviously 0, right? Because we have n squared and this is being squared again, so it's a huge number in the denominator. So we are going to plus infinity, and do we have to limit x? Well, let's maybe, for the ease of the argument, take it from 0 to 1. Can we do it? Yeah, we can. Alright. So what would be the integral of gn of x on the interval from 0 to 1 dx? Let us see what will happen here. Well, you see, if we take this one as z, what is z prime? Z prime would be 2 is coming down, 2n squared x. So exactly our numerator, which is nice. So if we put 0 for x, we're going to get 1. If we put 1 for x, we're going to get 1 plus n squared. So we're getting integral 1 to 1 plus n squared. Once again, look at this. This is dz. And this is becoming to z squared, right? So what we have is minus 1 divided by z from 1 to 1 plus n squared. And this is minus 1 divided by 1 plus n squared minus 1. And if we bring it to the same denominator, if we would like to have it, we are going to have, oh, we don't even need it. We can solve the parentheses. It's 1 minus 1 divided by 1 plus n squared. And now you see, if n is running towards infinity, we are getting to 1. So it's kind of strange thing that a function which is in the limit, the frequency of the sequence of the functions, is being 0, integrated over the interval 0 to 1, so we have no huge values of x, is giving 1. So this limit is 1. And, well, that's the problem. So we have three kind of troubles, as you can see, guys. The continuous functions, if we consider their limits, once again, right? The limit isn't necessarily continuous. All right. Then we have a pointwise convergent function with the limit of 0, where the derivative is unbounded. It's not existent, the limit. And the third case is we have a function where the limit is once again 0, but the integral over the interval 0 to 1 is given as 1, which is kind of contradicting our intuition. So what can we do? The thing is, the idea of the pointwise convergence isn't strong enough. It's comparable to the pointwise continuity, where we also figure out that at some point we need a stronger argument, we need a stronger tool, and this stronger tool was the uniform continuity, and the same idea is also being applied here. So in the next videos I'm going to explain what is the uniform convergence and how do we apply it. Thanks for watching. See you guys in the next videos. Bye bye.